Friday afternoon. Let's just start with a quick show of hands. How many of you are using containers at the moment? Actually, most of you, okay. And put your hands up if you think you've got a pretty good idea of what they are. Actually, pretty good. Excellent. That's really good. I think a lot of people hear terms like containers and they've heard phrases like lightweight virtualization, or maybe it's a bit like a virtual machine. And while that's kind of true in some senses, I think what I'm going to do this afternoon will hopefully make it really clear that when we're talking about container, we're really talking about a process that has some special characteristics, but really it's just normal Linux processes. So before I go on to sort of building one myself, let's have a look at some of the characteristics that we get when we run a container. I'm just going to use Docker in the kind of normal way, and I might do docker run, and let's say I do something like Ubuntu, and I can run a bash shell, for example. And I can see things like I have a root directory. This is the same virtual machine. These are two windows of the same virtual machine, but in the bottom I'm on my host, and it's a different root directory. I've even marked that root for host just for reference. So I can see what looks like a different file system from inside my container. If I look at the running processes, they've got low numbers. They start with 1. If I even look for all the running processes, that's the only set of processes I can see. From my host, I've not got that many more processes in this particular window. They've got much higher process numbers because I've been running this machine for a while. And there are loads and loads of processes here, including, if I get to the right place, we can see my docker run command. Now, if I do something like sleep inside my container, and I could look for that process inside, well, from the host perspective, and there it is. So from my host, I can see what's going on inside a container, and I think that's quite important. You know, when we think about what the isolation is. If I was running a virtual machine, I wouldn't be able to see from the host. I wouldn't be able to see guest processes like this. One last thing. Well, one last thing I will do is let's run that again. And just show that if we look at the user for this, we're running as root inside the container. I'm running as root outside the container as well, but typically, whenever you run a container, you're going to be running as root unless you've taken steps not to do so. But it's not just root inside the container, it is root from the host perspective. Okay, so we've looked at a couple of things about what happens when you run a container. What does it look like? It looks like it's got its own view of processes, it's got its own view of a file system, it kind of feels a little bit like its own machine, but from the host perspective it's not. So now I'm going to try and show you how that's created by building one up in some code. And I'm going to use 3 sort of features of Linux to do this. Namespaces, changing the root directory with chroot, and a thing called control groups, or C groups. So let's start with namespaces. And these are like a way of restricting what the process can see. When I start my process, I'm going to say create it with new namespaces for it could be any of these 6 different things. I'm not going to have time to do all of them. But when we create a namespace, I'm saying I'm just going to have an isolated view of just a subset of what the host has. And, well, let's start creating some code. Let's do that. Now, have we got any Go programmers in the room? Good. You will be my code reviewers. Thank you. And I will warn you now, this is not going to be like production quality, okay? So we're going to have a main function. I want this to, so when I did Docker run, I said Docker run and then maybe an image name, and maybe I can pass it some kind of command that I want to run inside that container. I used bin bash. Maybe there would be some arguments as well. When I run my Go program, I'm going to use go run main.go, which is kind of, that's going to compile and run my executable. So that's sort of the equivalent of Docker. I'm going to use a parameter called run for reasons that will become clear later. I'm not going to bother with specifying an image because, again, for reasons that will become clear later, but I am going to pass in command and arguments. So the first thing I'm going to look at is this parameter here, the run, well, argument, and that's going to be argument 1. I'm going to look at that, and if it's run, I'm going to call a function called run, and if it's anything else, I am going to collapse and tag. Okay. So I need a run function, and let's just start by printing out what it's going to do, because debugging is a good thing, right? So we'll say it's going to run, and then whatever I've been passed in as arguments to and on. So that's my command and potentially some optional arguments. Okay. So just to check that I can compile and run things, let's do go run main.go run, and I could say something like echo hello Malaga, and all it's doing is logging something out. Liz, this is not very impressive. Okay, let's have it actually run this command. So I can set up a structure that can describe the command I want to run. And I'm going to pass it the name of the command I want to run, and maybe there are some parameters. Okay. And then I have to wire up std in, std out, std because otherwise it would be really dull. So we just do 3 of those, and this is where I get very excited by multi-cursors. Oh, that wasn't mine. I got overexcited about multi-cursors, obviously. Okay, and then I can call a method to actually run the command. So it's not until I hit this run method that I'm actually going to execute whatever it is that I'm going to ask it to run. So let's just check that that works. And not only does it print out what it's going to do, it actually does it. It echoed hello Malaga, hooray. I can run some code. I could run, for example, a shell, like I did before when I was using real Docker. Can't really tell that I'm inside a shell, or you can't really tell that anything's happened because my prompt looks exactly the same. But we can see a few extra processes are running compared to when I wasn't inside my container. But at the moment, it's not in any way containerized, it's just a process. So I'm going to start namespacing with, the first namespace I'm going to use is, it's got a very fancy name. It's called the Unix Time Sharing System, which sounds really grand and important, and actually all it does is give you the host name, really. So let's say that I want to create some namespaces with this sysproc atra structure, and creating the new process uses a system call clone, and I'm passing in some flags for this that will be used on the clone call. I'm going to say I want to clone a new Unix time sharing system. Very exciting. So I run that, I look at the host name, it's the same host name as I have on the host machine. What if I try to change it? So let's say I call it Malaga for fun. I can change it inside the container now. The container. And it's been isolated from the host name for the rest of the machine. So I have in some way started to containerize things. Okay. So the next thing I would like to do is inside my container, no, the next thing I'd really like to do is make it so that I can tell whether I'm inside my container or not. It would be nice if I could get my prompt to change when I start that shell. And there's a kind of convenient call that I could do called set host name. Sounds promising, yeah? And I have to pass it in a list of bytes. Should I call it Malaga? Why not? Now, I can't do that there because where I've put that, it's after I've come back from running the command that I'm running, so it's too late. That won't take effect until after I've finished. So what if I did it earlier? What if I did it here? That's no good to me either because I haven't actually created my namespace yet. I don't get to clone the new process until we're inside this run function, and that's what's going to clone the new namespace. So what I'm going to do is kind of call this twice. So the first time is going to be called run, and the second time is going to be called child. And in the first one, we're not going to set the host name or anything, but we're going to create the namespace. We're going to call back into ourselves and or to run the same program again, and we're going to use something called proc self-exe, which I shall show you in a moment. And we're going to come back, instead of having the argument run, we're going to use an argument child. And I'm going to pass in all of the other arguments. And then I have to do a little bit of incantation go to make this work. So I have to turn this into a list of strings and append all the other arguments to it. Okay, so I come into run. I'm going to execute this same executable again, but with this new namespace. When I come in the second time, I'm using the argument child instead of run. And that time, I'm going to come through here. I'm not going to create a new namespace because I'm already inside the new namespace, but I can do things like set the host name, or at least I hope I can. So let's see if I've done that right. Okay, we can see from the prompt that I've been able to change the host name for my containerized child process. That's pretty encouraging. We also see 2 lots of that logging out of what I wanted to do because I'm running run the first time and I'm running child the second time. So suppose I want to fix PS so that I can't see the processes from outside my container. So there's another one of these namespaces. Namespace flag is clone a new PID, process IDs. That sounds quite encouraging. So let's try, let's log out what our process ID is as process ID, whatever. Get the process ID. And we'll do that in both the parent and the child. So the parent had some high number process ID because it's in the same numbering scheme as the host machine. But the second time, I've got process ID 1. I've started numbering again because I'm in a new process ID namespace now from my container, which is, well, that seems pretty encouraging. So you'd think I'd just see my processes inside the container, but sadly not. I can still see all the processes from the host. And the reason for this is because of /proc. So I'll do this on the host as well, just to see it's the same thing. So /proc is what looks like a directory, but it's actually what's called a pseudo file system. And pseudo file systems are a way for the kernel and user space to communicate through things that look like ordinary directories and files. So the kernel creates these things that look like directories for every currently running process. And it also creates things like, let's have a look at proc self, because I remember I just used proc self exe to run myself. If I run this a couple of times, we'll see it gets a new process ID every time. And if I look at the exe, it's showing me whatever I just ran, so it was ls in this case. So every running process has a directory, or what looks like a directory under /proc with its identifier and all sorts of interesting information underneath it. So let's have a look at, for example, I'm just going to pick one at random. Proc 1069. And we've got all sorts of information in here that the host can see about what the root directory is, what mounts this process has, all sorts of fun bits and pieces in here. Okay, so my container is looking at the same /proc as the host. And that's because it's got the same root directory as the host. If I want my container to have, or for PS running inside my container to only find the process IDs in that namespace, I'm going to need a proc pseudo file system that refers to that new namespace, which is kind of confusing. But what we'll do, we'll create a whole new root file system for my container, and then that will be a good place for /proc to live. On my host, I happen to have a copy of an Ubuntu file system. So it looks like sort of normal directories that you would have under root. I've identified it in this file called root for container. And I'm going to mount that, I'm going to change root inside my container to point to that. So, where I do this, we can do chroot, and it was under vagrant Ubuntu file system. Okay. I'm still in my container, so I need to quit out of it. Now, turns out that when you do chroot, you actually end up somewhere undefined. So I need to explicitly change my directory so that it knows where I am. We'll just change to root. Quit out of that, do it again. Yeah. Did I not say? Oh, chroot, that's not what I meant. Should be it. Nice. Okay, so now we can successfully, it knows we're in the root directory that we changed to, and if we look at it, it's that one that I've identified, it's this root for container. So I've got a new, my container can only see this set of files. It can't see anything further up the file hierarchy than this directory because it sees this as root. Even though from the host perspective, it's under vagrant Ubuntu file system. Inside my container, I can no longer see anything higher up than this directory. But I've got this proc here now, so that's kind of encouraging. Maybe I can do PS. I can't because I have to do one last thing, which is I have to tell the kernel to use this proc directory as one of those pseudo file systems. And it told me exactly how to do it. I'm going to mount proc as a proc pseudo file system type. So, very important that I get these in the right order. Proc, proc. You bored yet? Lots of procs, there we go. And I'm going to tidy up after I finish by unmounting this again, because they tend to build up. Okay. So now, when I do it, PS knows where to look. It knows to look in the /proc that I've got chrooted into, and it knows that /proc is a pseudo file system of type proc, so that's where PS is getting its information for. Hooray! We've successfully isolated the host name, we've successfully isolated the file system, and we've successfully isolated the process IDs. Incidentally, when I did that chroot, that's pretty much exactly what, when you have a container image, it unpacks the file system and then chroots into the base of it. So it's as if this directory was my container image. Also, kind of as a follow-on from that, once you're inside the container, it can only see files inside that from where it's chrooted to. So you can only run executables inside the container that it can find inside the file system. That makes sense. Okay, so we've looked at Unix time sharing system namespace, we've looked at process IDs namespace. We can have a quick look at the mounts namespace too. This is, let's run the term again. So I've got this mount of /proc that we can see inside the container. And if I look at the mounts from the host perspective, there will be loads and loads of them, but just the proc ones, we can see some host-related ones, and we can also see the one that's inside the container. We know that must be the container one because it's mounted at Vagrant Ubuntu FS. Now, let's add another namespace in here. This is called new. This one is called new NS, and NS stands for namespace. And my understanding of this is this was the first namespace they added into the Linux kernel, and they didn't really anticipate that they'd need any other ones, so they just called it new namespace, and then realized there were loads of other things that you would want to isolate as well. So, for historical reasons, it's called new namespace. Now, I also have to add in something called unshare flags for this one. Oh, I'm going to do clone. NS. So now that I have done that, I should still be able to see the mount point from inside the container. But it's no longer, I'll do that again here, it's no longer visible. I can't see the Vagrant Ubuntu FS one from the host perspective anymore. So it's no longer showing up in the kind of mounts list for the host. The reason why I needed to do this unshare flags thing is by default, all of the mounts are kind of shared. So even though they have their own namespace, it would also be saying, yeah, but share it with everybody anyway. So I have to explicitly say, don't share it in order to have it not show up on the host. That is not hugely useful in itself if you're root, because if I do something like the sleep thing again, so we can find the process from the host perspective, sleep. And if I look in proc 17756, we can see there are things like mounts, and I can cat that directory, that file rather, and I can still, so from the root on the host can still see that mount exists. It's just not cluttering up its own list of mounts. So from a normal user's perspective, they might not see it, but as root, I can definitely see it. Okay, so that's 3 out of the 6 namespaces that we've isolated in my kind of pseudo container here. You go through a similar process if you want to isolate network, so that your container can only, or has its own view of network interfaces. User IDs as well. I mentioned before that we're running as root inside the container. There is now a user namespace, so you can have your own perspective inside the container of what user IDs mean. And you can also isolate inter-process communications so that they can only be happening within a container. But let's move on from namespaces to control groups. So if namespaces tell us what you can see, so by using namespaces I can restrict what things my container can see on the host. And we can use control groups to restrict what resources I can use. And then resources like the amount of memory, the amount of CPU, how many processes I'm allowed to run, that kind of thing. And we configure them using another one of these kind of pseudo file system interfaces. So this is in, let's look at sysfs cgroup. And these are the kind of things that you can configure, the cgroups that I can configure on this host. And if we have a look at what's inside memory, well, mostly we get a load of parameters. So I could look at memory limit in bytes is a good one. So that's basically all the memory inside my virtual machine. So by default, any process can use all of that memory, and that would be fine. Now, if I want to limit a process, or I want to create a control group, I'll do that by creating a directory inside, I have to do it for each of the resources that I want to constrain. And we can see Docker has created a directory inside memory. So this is how Docker is going to limit memory if it wants to for particular containers. We can have a look inside there. Oops. Sorry, the memory. And we get all the same kind of parameters inside that directory as well. The kind of, every time you create a child directory, you inherit the same settings from the parent directory. And if I run let's run an actual Docker container. So let's do the same as I did before. Ubuntu, create a shell. And my container has got this name that begins D930. And if I now look inside that memory Docker, Docker has created a directory corresponding to that. And this is because it wants to create a C group for this container. And if I look inside that one, D93, whatever, actually, let's see, let's take the, so if I look at the memory limit in bytes, and that's not being constrained either, it's still like a massive number. But if I do the same thing again and I actually limit the amount of memory, so let's say I limit it to 10 megs, I've got a different container name now, so it's 69FC. So let's look at the memory 69FC, memory limit in bytes. And now that's been constrained to, that's going to be about 10 meg. So that's how Docker has configured to tell the kernel, I don't want you to allow this process to have any more than this number of, or this amount of memory. Also, the other thing that we do is, or the other thing that we might need to control is how do we know, how does the kernel know which processes are kind of limited in this way? And if we do the same thing that I've done before, we do a sleep, and we find that sleep process ID is 18148. And if I look inside cgroup procs, yeah, we can see that process ID is inside this cgroup procs file. If I want to add a process into a cgroup, I have to write its ID into this file. So let's have a go at doing that. Now, I am going to, I've already, hopefully, let's find I've got a function that I have written earlier, just because there's quite a lot of it. So this CG function, rather than doing memory, I'm going to use the process IDs limit. So this limits the number of processes. You can only run so many processes in inside this C group. And I'm going to create a C group called Liz. And inside that, I'm going to write the value 20 into a file called PIDSMAX. So that's the file that I need to configure to say what is the maximum number of processes I'm going to allow in this C group. The notify on release flag just says I can, you can get rid of this when this C group is finished. And then importantly, I'm going to write into that C group procs file, just like we just saw Docker had done. I'm going to write the current process ID into that file. So that should add this current process into that C group. I need to actually call that function from my child, otherwise it would not be very effective. Okay. So if I run that again, and we can just check that we're doing this. I want to make sure that my process ID really is inside the C group. So if I look inside PIDS, there's Liz, and if I just make sure PIDSMAX, PIDSMAX should be 20, yeah, and let's check whether or not my process was correctly added, and I'm looking for 18280, and there it is. So I'm reasonably confident that I can only have 20 processes inside this C group. So I can only run 20 processes inside this container, which could come in handy if I want to do something like this. Has anybody seen one of these before? Okay, a few hands. This is what's known as a fork bomb, and it's a bash script that you only want to run in very careful circumstances. So, what it's doing, it is defining a function called colon. And what that function is going to do is call colon, pipe the results into colon, and run that in the background. And that's the definition of the function, and then you just invoke it. So that's just going to keep recursively creating more and more and more and more and more functions, which is not a very healthy thing to run on your servers, particularly in production, and it is an attack. Let's do it anyway. Okay. And it's obviously failing pretty quickly to be able to create child processes. But if I look from the host perspective, here they are. We can see there's my go run main.go, and it had a child process, that's the child. And here are some bash function or bash processes. We're never going to see more than 20 of those, because I've successfully contained it within a control group, in a C group. And this is why people use C groups on their containers. If you have many containers running on a machine, you want to make sure that each container can't use all of the resources, whether it's the amount of memory, the amount of CPU. It's a good way of making sure that either kind of by accident or through somebody being malicious, that nobody sets off a fault bomb inside. Well, if it sets off a fault bomb inside your container, the effect is constrained within the container, as we're seeing here. The rest of my host is functioning perfectly fine, because it can cope fine with 20 defunct processes. Okay, so we have basically successfully isolated using namespaces. So my container only has a restricted view of the world. We have used C groups to show how we can restrict the resources that it can access. And we're seeing how that can protect us against certain types of attack or kind of bad programming. And we've done that in, that's about 77 lines of code today. So Docker is a little bit more than that, but, but that's kind of the gist of what Docker's doing. Okay. There is a version of that code on my GitHub repo at Containers from Scratch. So I do very much encourage you, if you want to explore it into this kind of thing, it's good fun. Try for example, adding network namespace or something. It's good fun. The other thing I wanted to mention, so quite a few mentioned that you are running containers. Put your hands up again if you're using containers. Okay, and leave your hands up if you are running vulnerability scanning on those containers. A smaller number, right. So one of the things that we do at Aqua is vulnerability scanning, so that you make sure that you are not running known exploits in your container code. And this microscanner is a free tool that we've recently produced, so you can basically scan your containers for free using our kind of commercial grade scanning tool. We actually do this in quite an interesting way. You build the microscanner into your Docker file. So you can run the scan as part of your build, and if it finds any high severity vulnerabilities, you can fail the build, and then you sort of automatically can't run that code, so that's kind of nice. It is pretty new, and I would love it if you try it out and send me any feedback. We would love to hear about it. With that, I really hope that that has kind of explained something about what containers are and how they work, and given you some thoughts about protecting them from vulnerabilities too. Hopefully we have a bit of time for some questions as well.